Dear colleagues and guests, today I'll be presenting our comparative analysis of camera calibration algorithms for football application, a field that sits in the intersection of computer vision, sports analytics, and real-time data processing. In the, water, in the world of modern football, data is king. Teams, broadcasters, and analysts constantly seek deeper insights into player performance, tactical patterns, and game dynamics. While traditional methods like body-worn sensors can provide this data, they come with significant drawbacks. They are expensive, potentially uncomfortable for players, and not always practical, especially in competitive matches. This is where computer vision solutions come in. By using video footage alone, we can track player positions and movements through the match. However, the cornerstone of making this possible is an accurate camera calibration, the process of transforming 2D video coordinates into meaningful 3D position on the field. Our research examined the generation of calibration approaches, traditional static methods using vanishing points, dynamic calibration techniques, modern machine learning solutions. We'll explore their strengths, limitations, and most importantly, the exciting opportunities that lie ahead of improving these systems. By the end of this presentation, you will understand camera calibration is crucial for football analytics, how current solutions stack up against each other, and where future research could take us in the making these systems faster and more accurate. Before diving into specific calibration methods, let's understand the mathematical foundation of how camera captures 3D scenes into 2D image. At the heart of our work is pinhole camera, a mathematical abstraction that describes how 3D world points are projected onto 2D image plane. While modern cameras are far more sophisticated, this model provides an excellent starting point for understanding the projection process. The basic perspective projection can be expressed through the three key components. First, we have internal parameters represented by K matrix. This matrix encapsulates the camera intrinsic parameters, the focal length, the skew factor, and the principal coordinates. Second, we have the rotation matrix R, which describes how the camera is oriented relative to the world coordinate system. Think of it as camera is looking. Third, there is a translation vector T, which represents the camera position in 3D space, essentially where the camera is located. These components together is what we call homography matrix, a mathematical transformation that maps points between the football field plane and the image plane. Understanding this matrix is crucial because it allows us to convert between what we see in the broadcast image and actual position on the football field. Let's move forward to see how different method approaches challenges determining these parameters. Let's examine the foundation methods that pioneered camera calibration in sport, starting with static approaches and moving to the dynamic solutions. Static methods represent first generation of calibration techniques. We have two primary approaches here. First, the vanishing point-based calibration. This method relies on identifying where parallel lines in the real world appear to converge in the image, what we call vanishing points. While elegant in theory, it has limited practical applications in football because it typically requires special calibration patterns that aren't present on the football field. Second, we have model-to-image registration, which works by detecting lines on the field and matching them to the known field model. This approach shows promise, but it needs a sufficient number of visible segments to work effectively, something we can't always guarantee during a match. Moving to dynamic methods, which represent significant step forward. The quality-based tracking method approach uses feature matching between consecutive frames to maintain calibration as the camera moves. While innovative, it faces critical challenges, error accommodation over time. Small mistakes in each frame can compound into significant inaccuracies. To address these limitations, combined approaches were developed. These methods integrate multiple data sources and techniques, achieving better accuracy but at the cost of increased computational complexity. The key insight from studying these traditional methods is that while they laid crucial groundwork, they all face significant challenges in real-world football application, either in terms of accuracy, reliability, or processing speed. Let's move on to see how machine learning approaches have addressed these limitations. Also here you can see examples of calibration via static method, calibration via dynamic method, and same for the hockey, because usually hockey is also presented in these papers. Machine learning breakthrough. The major breakthrough in camera calibration came in 2017 with machine learning. Unlike traditional methods that relied on detecting line intersections or tracking points, this approach used marker random field framework to understand the football field holistically. It recognizes three elements: the field surface, lines, and circles, and could function even with partial visibility. Trained on 9 stadiums, it achieved IU score of 0.86 significantly outperforming earlier methods. This success paved the way to future deep learning approaches in camera calibration. On the right part of the slide in figure 8 you can see their results. Building on success of 2017 breakthrough, researchers developed an increasingly sophisticated approach using multiple neural networks working together. This combined approach addressed several key limitations on earlier methods through some clear innovations. The main innovation came in how they handled noise reduction, a major challenge that plagued earlier methods. They implemented two-step noise reduction process. The first step used color-based field segmentation to move the crowd from images, sometimes previously confused calibration systems. The second step employed faster RCNN to detect and remove players from the scene. Think about it how this solves one of the biggest problems we saw in traditional methods, where a player standing on the field lines would disrupt the line detection process. For matching features between frames, they developed a three-pronged strategy using chamfer matching, hog description, and CNN-based feature matching. This redundancy helped ensure reliable performance across different conditions. But real game changer came with introduction of HRNet v2 backbone architecture. This represents our current state of the art and number of impressive, processing each frame in just 33 milliseconds. To put that into perspective, remember how the earlier dynamic methods we discussed, their processing time was just a few frames per second. The accuracy improvements are equally impressive. On the World Cup dataset, it achieves a IU score of 0.96 for partial field coverage, and for TSWC dataset, it reaches 0.98 for the whole field coverage, compared to the 0.86 score from the 2017 breakthrough. So, as a result of our comparative analysis, looking at traditional methods, both static and dynamic approaches we discussed earlier, we encounter a consistent problem. Many papers don't even specify their accuracy metrics. When they do provide metrics, they are often limited to specific conditions or parts of the field. Yes, these methods have one significant advantage: they are relatively simple and to implement. They don't require specialized hardware or extensive training data, but their limitation in field coverage and accuracy make them increasingly inadequate for modern applications. In contrast, machine learning methods have shown remarkable improvements. We have seen accuracy scores as high such as 0.96 IU, a level of precision that was unthinkable with traditional approaches. These systems can handle varying lighting conditions, partial field occlusions, and different camera angles, situations that would completely confound traditional methods. However, this is important. These improvements come at cost, significantly higher computation requirements. This brings us to the crucial question: where do we go from here? Our thesis identifies several promising directions for future research. First, the significant potential of model optimizing techniques that haven't been fully explored in this domain. These include pruning, essentially removing unnecessary neural connections, quantization, reducing the precision of parameters to speed up the processing, and knowledge distillation, transferring knowledge from larger models to smaller, more efficient ones. Another exciting direction involves exploring smaller variants of the HRNet architecture. The smaller version could potentially offer similar performance with lower computational requirements. The goal is clear: to maintain the high accuracy that is achieved while making the systems more practical widespread deployment. This means not just optimizing the models themselves, but also exploring hardware-specific optimizations and implementing sparsity techniques to reduce computational overhead. The future of this field lies in finding the right balance, keeping the robust performance of machine learning approaches while making them more accessible and practical for real-world applications. It's just not about pushing accuracy higher, it's about making the system viable for broader adoption. Thank you for your attention.